Conventional soil science would say that you can't change soil organic matter in our lifetime. What we've been seeing, and the reason that we're so interested in this, is that producers that have been doing new practices, their soil organic matter is going up quite dramatically. And so if you're seeing 5% change in organic matter over 20 years, or we were down at the Waldron and we saw a 3% change over 5 years of implementing new grazing management, it's shocking and very exciting. But soil organic matter is 58% carbon. Through that microbial interchange, when there's enough carbon flowing into the system through photosynthesis from all of those plants, the mycorrhizal fungi will make this substance called glomalin, and it's kind of like a glue. It sticks a whole bunch of little bits of soil together to create what they call as an aggregate. The mycorrhizal fungi will enable it to be resistant to water. So if it's not there, you may have an aggregate that forms, but when water comes down into the soil, it'll just like explode, and it clogs up all those pore spaces. So it changes our water infiltration and everything else. But what that glomalin will also do is it protects the carbon inside that aggregate from the microbes eating it and then just respiring back out the CO2. And so that process, when there's enough photosynthesis happening and there's enough carbon in the system, we start to stabilize carbon in the soil at rates that we didn't really realize. Glomalin was only discovered in 2004, and so I think that that's why we're still trying to piece together how these systems are working and what's actually happening when we're seeing these vast improvements in soil health through new grazing management systems or other regenerative agricultural processes. What we're really seeing is that it's the microbial community. Just like we have a lot more microbes in our system than we have human cells, like I think it's more than a 10-to-1 ratio. The soil is that mineral matrix, and it's the clay, sand, and silt, but it's really the microbes within the soil that make it alive and that make it function. The biggest thing about photosynthesis that I think we don't really focus on is it's a CO2 molecule. Like we always talk about, plants eat CO2 and they give out oxygen, but it's really the CO2, the photosynthesis splits that molecule, and so it releases the oxygen, but then it takes the carbon from the CO2, and that's what plants use to build their body and do all of the things that they do. But then about 40% of that carbon actually goes out through the roots as exudates, and it starts to feed the microbes. But what we see, especially in like complex systems, is that the plants will develop an association with mycorrhizal fungi, and that becomes like the subway system of the soil. And so that carbon will come down from, say, a grass plant, and it will travel along the mycorrhizal fungi, and along the way there's phosphorus solubilizing bacteria that lives on the mycorrhizal fungi, and there's like a door almost that opens. The mycorrhizal fungi will give some of that carbon that came from that grass plant. It will trade that carbon for the phosphorus from the phosphorus solubilizing bacteria, and so then that phosphorus travels along the mycorrhizal fungi to get to a legume plant, and that legume plant will go through the process to fix nitrogen using the phosphorus, and then it makes the nitrogen available to the mycorrhizal fungi that it can then take back to the grass plant. And there's this beautiful exchange, because without the phosphorus, the legume can't do what it needs to do to fix the nitrogen for everything else. Also, what we're seeing as those water-stable aggregates form is that it allows for much better infiltration of water into the system. So instead of when it rains, it runs off, the infiltration rate is better. But also because there's all these little bits and pieces, the water comes in and it has to go through like a really windy route. And we know from looking at rivers that wind go much slower than rivers that are straight through. And so those water-stable aggregates hold water in the root zone where we need it. And then also through a lot of these regenerative agricultural practices, we're making sure we have a cover on the soil. And so that's reducing the amount of water that's just evaporating. But more than that, it's also trapping the water, because when microbes are cycling, as anybody knows that's ever been in a car in the winter with a bunch of people, there's humidity that builds up. And so microbes do the same thing. And if you can contain that moisture, sometimes that's the moisture that you need for germination if there hasn't been any rain. And so those microbes actually produce moisture even when it's not falling from the sky. Our prairie soils were historically, before tillage agriculture that started at the turn of the century, were 9 to 14% soil organic matter. I think they're probably sitting between 1 and 9% in the province today. Tilling the soil, it kind of activates the soil, and then the microbes can eat it, and that does create a flush of nutrients. And so before we had chemical fertilizer, that was the process that we were using, but we were using historical carbon. And so by building carbon back up into our soil and regenerating those soils, we start to build up that resilience that we had historically and take the pressure off of needing chemical inputs in the same way. Like, we may still need them, but we don't need them to the same extent, because as our soil health improves, then we'll see less of a need for certain inputs.